Hello, this is the next video in a playlist that I'm calling Hypothesis Test. And we are going to develop a simple versus simple test to test whether a die is biased or not. Is it rolling all the numbers with equal probability, or is it rolling a few of the numbers with higher probability? We're going to develop an approximate alpha level test using asymptotic theory. So let's let yi be the outcome of a die roll. And so a die takes on values 1, 2, 3, 4, 5, 6. So each observation is an indicator variable on what was rolled. So there's all zeros and one, and where that 1 is tells us what we rolled. So in this case, since the 1 is in the second component, means we rolled a 2 on the die. Now the probability, we're going to let capital PI equal the probability that we roll an I. Now yi is what's called a multinomial distribution with n of 1, and then with these probabilities P1 through P6. We're going to collect a sample of size n, and then the probability mass function for I at yi is f of yi, which is equal to P1 raised to the y1. Now, this y1 is the component here. P2 raised to the y2. So this component's a 1, so that would be a 1. The rest are zeros. Now we're going to let x be the sum of these yi's. Right, we're collecting a sample of size n, and then if we take the sum, it will tell us how many 1s we rolled, how many 2s we rolled, etc. And it's also a multinomial distribution with parameters n and P1 through P6. And these are the probabilities, of course, of rolling a 1 or a 2 or a 6. The probability mass function for f, so f of x, this is the combinatorics n choose x1, x2 to x6, and then p1, x1, p2, x2, and p6, x6. And so the hypothesis that we want to test is the probability of rolling any number the same, is it 1/6, versus is there some other probability? And we're going to, let this be whatever that is, that other probability. And of course, according to Neyman Pearson, we set it up like this, and this is the most powerful test for a given, alpha level. And phi of x is 1 or a 0. And if the likelihood ratio is greater than some value c, we reject the null hypothesis and accept the alternative. If the likelihood ratio is less than that constant c, then we accept the null hypothesis, or do not reject it. Now the likelihood ratio, f of 1 and f of 0, would be this. The coefficients out front cancel each other, but when we're under the null hypothesis, we have to put in those hypothesized probabilities raised to the x. And under the null, we're assuming they're all 1/6. And again, raised to the x1, x2, all the way to x6. Well, we combine, these terms that have an x2, and then that invert and multiply, and so we get this expression right here. So now, if we take the expected value of phi under the null hypothesis, that represents the probability of a type 1 error, or alpha. And we're under the null hypothesis, so the probability that the likelihood ratio is greater than c, assuming the null hypothesis is true. Now, this piece is this piece. So if we take the log of both sides, then this becomes, some other constant, c prime, and then the log of a product's the sum of the logs, so we get this, and then that exponent can be taken out front. So this can be thought of as a linear combination. So this probability is exactly this, where L transpose X where L is just these coefficients out front, and X, of course, is our multinomial variable. Now a note is that this L prime X is approximately normal, and we'll prove this on page 2 with some, n times mu and n times sigma squared, where mu is this L transpose P, where this is the hypothesized probabilities, and sigma squared right here is just L transpose sigma L, where of course P, the vector P, is the hypothesized probabilities. Sigma is the covariance matrix for X, the vector X. Now, because this is approximately normally distributed, according to this, we can subtract the mean divided by the standard deviations of both sides, and then we get a new constant. And that constant, well, this is Z, distributed with the standard normal. And we want to find this value such that it makes it, alpha level. So if we, in the standard normal, if we create this variable Z, or this constant Z alpha, which makes the area in the tail to the right alpha, that's what this represents. Then of course we can multiply that and add this over, and we get this. So the probability that this linear combination is greater than this cutoff is alpha. And that's how we create this alpha level test. So to look at the power, it's the expected value of phi, but assuming the alternative is true. So the probability that we reject is the probability that this linear combination is greater than this critical value that we just developed, but assuming the alternative is true. Now if we subtract the mean, now remember we have to assume that the alternative is true, and divide it by the standard deviation, we get this. So then that becomes a Z random variable, and distributed standard normally. So this would be, the subtract the mean, and this is divided by the standard deviation. So the probability that Z is greater than this, that's power. Now, to look, so to rewrite this test, so our test function is 1 or 0, depending on if the likelihood ratio is greater than this critical value, or we do not reject the null hypothesis if it's less than this critical value. Now, using specific examples, if we let P1 through P6 equal 1/6, so it's an unbiased die, versus the probability, and I just made these up, so that the probability that we roll a 5 or a 6 is 0.22, and the probability we roll a 1 through 4 is 0.14. So those sum to 1. We want an alpha level 0.05 test. That means Z alpha is 1.645. Our linear combination, our L vector, is the natural log of 6 times 0.14, which is this, all the way, to log of 6 times 0.22. We're going to let n equal 25. So the mean under the null hypothesis is this. We take a linear combination, which is this, and then times each of these probabilities, and we get minus 0.0237. The variance, so sigma 0 squared, is this formula. It's the sum of the pi times the Li minus mu. And actually we'll prove this. That's 0.0459, and then you plug it into those values into here, and this is our test. So phi, our test function, is a 1 if the linear combination is greater than 1.16, and we do not reject if this linear combination is less than that value. And that's an approximate alpha level test for testing whether the die is biased or not. So now let's go through some technical derivations and then call it quits for this video. But prior to this, I have a video called the multivariate normal distribution as an approximation to the multinomial distribution. And in there, we proved that X is a asymptotically multivariate normal with mean in P and variance covariance matrix in sigma. Now, if we look at a linear combination of these X's, then based upon this and that video, then the mean is just a linear combination of these probabilities. And then when you look at the variance covariance, you bring this out front, the variance of that, and then that transposed out back. And so this is the multivariate normal distribution. So this is multivariate normal asymptotically. So the mean is L prime P, when that's the vector of probabilities of the die, which it's the sum of Li Pi. Now to look at the sigma squared, which in the previous notation here. So sigma squared is L transpose sigma L, which, since this is a quadratic form, it's just this, where sigma is the covariance matrix. Well, in this video here, we derived this matrix. And when I and j are not equal, it was minus pi pj. That was the covariance. Of course, then we have to carry these along. And when I was equal to j, then it was pi times 1 minus pi. And of course, we have to keep those together. Well, here, what we do is if we multiply this into there and then this into that, we take the second one, so pi times pi, and we put it in this, then here we're just left with Li squared pi, and that second one gets put in here. So we don't have to say I not equal to j. We can just keep them I and j. Well, if we take out the pieces that are not indexed by j, we get this. But this right here is mu, and this is mu. This we bring down. Now notice here we have minus 2 mu squared plus mu squared. So this is minus mu squared, which is what this is, right? But I wrote a 1 out front because it doesn't change the multiplication, but I did that. So we take this, carry it over. We have minus 2 mu, but this linear combination was mu. And then here we take 1 times mu squared. And the sum of the probabilities is 1, so that multiplying 1 times that doesn't change it. But we can factor out a pi of each term, and we're left with this. But this is a quadratic, which is this. And so we're done. And that's what we wanted to show. Now I'm going to create an R video to compare this test with an approximate chi-squared test to see which one has better power and maintains the alpha level better. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.